So we have done till now, I think, uh, electric field now. So today we are going to start with a few questions on electric field, okay? So that you're able to understand on those things. Just give me a minute. Okay, just give me a minute. Okay, am I audible now?
हाँ सर.
Okay, so see, हम लोगों ने कल तक कर लिया था integration technique, right? Okay, we'll do Gauss law also, but let us do a few questions and then we'll move to Gauss law also. So till now we have done that how electric field is calculated, and one of the calculation we did. Okay, one of the calculation we already did. Okay, so in order to calculate electric field, we have till now discussed something called as integral method. Okay, an integral method. What is the methodology? As I stated, that Coulomb's law is only valid for static point charges. Up now, since it is valid only for static and point charges, so and what is electric field? Electric field at a point P. Let's say at point P we want to find electric field. At point P, the electric field is equivalent to finding the force. Find the force exerted at point P at point P. और वहां पे point P पे क्या होगा? At point P where and you can say uh, where an unit coulomb charge is placed. Okay, so where an unit coulomb charge is placed, uh, unit coulomb charge is placed. So basically, in order to find electric field at any point, what you need to do, you just need to place a unit coulomb charge, and at that unit charge, whatever force is exerted, that particular expression gives you the field at that particular point. Also, I discussed what is field. Field is something that is characterized by the value in the space. Okay, so for a particular x, y, z, there should be a fixed scalar number. If there is a scalar number, then it is called as the scalar field. And if there is a vector also, that is a direction is also associated. Uh, let's say I told you one example that if one has to find, let's say in whichever room you are sitting right now, if one has to map temperature as a function of x comma y comma z, then this particular thing would be called as a scalar field. And if one wants to find what is the velocity of the air, or you can say the curl of the air, or you can say the rotation of the air, which is propagated by your fan right now moving in your room. So basically, you know that direction sense would come. So at any point, there would be some magnitude also as a function of x, y, z. That is there would be a magnitude of let's say velocity vector, if I'm speaking in terms of x comma y comma z. So there would be, for every x comma y comma z, there would be some magnitude, and there would be some direction also associated. Such a thing is called as vector field. So electric field is a vector field. Okay, electric field is called as is a vector field. Now you see, one thing we have already done. We have found electric field due to an infinite line of charge. And the electric field due to infinite line of charge, I discussed on that particular day by you can say, basically, if there is an infinite line of charge, and let's say the charge density was given as lambda, and we wanted to find at a distance r or x, I gave you that day, at a distance r which is perpendicular to this line of charge at point P, we want to find electric field. Then electric field at point P is in the radially outward direction and given by lambda upon 2 pi epsilon naught r cap. I hope it is clear. Okay, this is first of the things. Now you see, once you know this technique, let us try to find electric field due to a ring at a point P, distance x from the center of the ring. Let us try to find electric field at point P at distance x from the center of the ring, and this is basically perpendicular to the plane of the ring, or you can say on the axis of the ring. Is that clear? So let us say that total charge content is q. And let's say the radius of the ring is capital R. Now how to do? Let us take a small differential element dq, and how dq would be divided. So q upon 2 pi r would give you the total uh, charge density into, let's say it is in the distance, let's say ds. So in, let's say, fragment ds, this particular charge dq is contained, and because of this charge dq, at this particular point the electric field will be in this direction, right? And exactly at the diametrically opposite corner, if you take another differential element, you will find by symmetry that this will give you the field in this direction, right? Is that clear? So by symmetry, I know that net electric field will be dE cos theta. And what is theta? Theta is this. I hope it is clear. Harshit, is that clear?
हाँ sir.
Okay. So only dE cos theta will exist, because dE sin theta will not exist. The vertical component would not exist. Okay. So the net electric field will be given by the integration of dE cos theta. And what will be dE cos theta? It will be simply k dq upon this particular distance. This will be r square plus x square की power 1 upon 2 का square. So basically I would write it as r square plus x square, and into I think what is cos theta? Cos theta would be simply x divided by root over x square. So this will give you 3 volt. So if I have to integrate this up, so this will be it. And so net electric field due to this charged ring. So net electric field due to this charged ring at a distance x on the axis of this ring would be equivalent to k dq. Dq can, if you want to write, you can write it as k capital Q divided by 2 pi r into r square plus x square raised to power 3 by 2. X is here, and then you will have ds and this integration. I hope it is clear. And if you see, you are integrating with respect to ds. Ds is what? Ds is differential length element on this ring. If you add all this ds, what would you get? So if you integrate this entire ds, what would you get? You will get the total length of the ring. And what is the total length of the ring? It is equivalent to the circumference of the ring. Isn't it? And which is again equal to what? 2 pi r. So basically you will get k capital Q x 2 pi r divided by 2 pi r, and then you have this. So this gets cancelled. So to net electric field will be given by kq x upon r square plus x square raised to power 3. I hope it is clear.
Yes sir.
Okay. Now just try to find a question. So what would be the electric field at the center? What do you think? What would be electric field at the center? What do you expect the electric field to be? What do you expect electric field at the center of the ring? See, if I just make a diagram in this sense that you can get. So basically, if I make it in this fashion, okay. So what would happen if I just place a positive charge here, unit positive charge here? So if let's say this is my differential element ds, it will push the charge in this direction, and exactly at diametrically opposite corner you will have another ds element where there would be elemental charge dq. This will push the charge in this direction. Similarly, this will push in this direction, and this particular diametrically opposite corner, this particular dq would push the charge in this direction. So net electric field, you can expect it to be equal to what? 0 at the center of the ring. Yes or no? you could have easily assessed by here putting x equal to 0 also. So in order to get on exactly at the center of the ring, you should have x equal to 0. So your electric field net would be equal to 0 if you place x equal to 0. And at a very far away distance, at a very far away distance, if you want to calculate, that is, if x is way too greater than r, basically, if you're going very far away, so your x will be dominating. And if x is dominating, you can take x square common out from here. So you'll get x cube, and this will give you electric field net as kq upon x square. I think this is quite easy to find. You'll simply get kq upon x square, which is equivalent to the point charge. Like, for example, if you go very far away, and if you want to calculate the electric field at a very far away distance, you'd find that electric field is almost equivalent to the electric field of the point charge, isn't it? So if you have a point charge q, and if one wants to find the electric field due to this point charge at a distance x, then this particular electric field will be equals to kq upon x square, isn't it? So if you are going very far away from the ring also, and if you want to calculate electric field at a very far away distance from the ring, then electric field at that particular point is equivalent to electric field due to point charge at that particular distance. So for example, if this distance is x, and so this particular ring, you can just take it as a total charge capital Q and just place it here. Is that clear? So basically this happens. Now, if one asks, what is the distance where maximum electric field can be expected, where the electric field would be maximum? What is the distance x where electric field is maximum? How would you find it? Okay, so in order to find that electric field being maximum or minimum, one can use the condition for existence of maxima and minima. For the condition for existence of maxima or minima, that is for the condition for the necessary condition for the existence of a local minimum or maximum, you just have to differentiate this electric field and place it as 0. So at the point of local minima or local maxima, the derivative becomes 0. Is that clear? So if you just calculate it, you will get that x should be equals to r upon root 2. This is something that you can do on your own. So I'm leaving it to you as an exercise. Is that clear?
Yes, sir.
Okay. And if you want to find the electric field at this particular point, just you need to do what? You just need to place at x equal to r upon root 2. And if you place x is equal to r upon root 2, the answer that you will get is q upon simply, I think this is the answer, 6 root 3 pi epsilon naught. And then you can simply place, I think, r upon root 2. And this will give you r. So this is the electric field maximum. Where it is on the axis of the ring. It is on the axis of the ring. And specifically at the distance r upon root 2 on the axis of the ring. And you can find that. Is that clear? I hope it is clear now.
Yes, sir.
Okay, good enough. Now let us try to find, let us instead do a half ring case. Okay, I'll give you a few minutes to think about it, then I'll start. Okay, so instead of full ring, I'm making a half ring now. Instead of full ring, I'm making a half ring. I should make it with the things. So that it will look good then. Let me try it. No, not come good out of it. I think just keep chalo aise karte. So I want to so instead of ring, now I'm considering the case of a half ring. Okay, so a half ring of, let's say, radius capital R I'm talking, and let us say it is uniformly charged. Let us say it is uniformly charged with I think charge capital Q, and we want to find electric field strength. We want to find electric field strength, we want to find electric field strength at the center of this half ring. So instead of full ring, now you have a half ring. And we want to find the electric field strength at the center of the half ring. So basically, let's say this is my case. I don't know how to make it in a good way. एक मिनट यार, इसको देखते हैं, 2 मिनट रुको. Okay, let us try to make if I can get some shapes or something. इसको कैसे क्या करेंगे? Yeah, and even if I delete it, I cannot delete now. चलो देखते हैं. हाथ से बना. Let us make it using our hands only in the best possible manner. ठीक है, so I'll be making a half ring. So basically it will be a semicircle. Okay, so this is a semicircle, and we want to find this at the center. At exact center, we want to find the electric field at this particular point. Okay, we want to find electric field at this particular point, given that the radius is capital R and the total charge is capital Q. So let us say this particular ring is uniformly charged with the uniformly charged, and the total charge is capital Q, radius is R, and we want to find electric field. How to find it? So what I would do, I would just take a differential element d theta here. Sorry, I'll just take a differential element here. So what is the total charge contained here? So let us take that, let us say that total charge is dq, which is equivalent to writing q upon pi r into, what is the length here? So let us say at angle theta, we are assuming some angular width d theta. Okay, so what is the length here? So length would be simply r d theta, isn't it? Yes or no? So charge contained in this particular differential length element will be q upon pi d theta. Is that clear, Arshad?
Yes, sir.
Okay, good enough. पक्का ना?
हाँ सर, समझ में आ गया.
Okay, good. So now, if you just take another just symmetrically situated, if you just for the sake of understanding, I'm doing it. So for example, now if it was theta, just take a symmetric consideration, and you would see that the net electric field that would be added now would be the vertical component, not the horizontal components, because horizontal component would get cancelled. Only vertical components would survive. So by symmetry, I would write, so here I'm writing, by symmetry, only vertical components would survive. Okay, only vertical component would survive. And what is that vertical component? The vertical component here would be equals to d sine theta. So the net electric field, if I want to calculate, it will be simply d sine theta. Okay, not d sine theta. D sine theta. If this is theta, then this will be theta. This will be 90 minus theta. So basically, only d sine theta will survive. Is that clear? If at all you are doing from now again, I told you on that particular day itself now, if I want to integrate from 0 to pi by 2, then what I'll do, I will take integration limits from if I'm writing instead of d cos, if let's say d sine theta I'm writing, so by symmetry if I'm writing d sine theta, good enough. But if you are actually adding these two components and writing 2 d sine theta, then you would integrate it from 0 to pi by 2, because that would mean that every differential element that I'm taking in the angular, from the angular region, that, or you can say from angular, you can say theta varying from 0 to pi by 2, you are actually assuming symmetrically opposite corner, only symmetrically opposite or symmetrically situated differential element. So for example, if I am taking this dq, I'm considering another dq which is symmetrically placed to it. So if that is the case, and if I'm writing 2 te sine theta, that implies I'm taking this also, I'm taking this also. So then in order to avoid the duplication, what I would do, I would only integrate from 0 to pi by 2. If I integrate from 0 to pi, then what will happen? This will be a wrong thing to do, because if you're writing 2 dE sine theta, it implies for this dq, you have taken this dq also, and then you have written the component. If you are writing just dE sine theta, then integrate it from 0 to pi. I hope it is clear. So just don't make this mistake. Otherwise, if you're writing 2 dE sine theta, that implies you are adding the components and then writing 2 dE sine theta. So when did you do it? You did it when you were assuming dq and another dq also here. So if you are doing that, then only integrate from 0 to pi by 2. Because in covering from 0 to pi by 2, you have covered this particular side and this particular side also. So just, I hope I am able to explain you. Okay.
हाँ सर.
Okay. And what would be the electric field at point 2? This will be K dq. And what is dq? It is q upon pi, and this will be d theta. K dq divided by 1 upon r square. Right? K dq upon r square. This is the formula. Okay. Now,
हाँ सर.
okay. So what has happened? I don't know where is the mistake. Have I made some mistakes there? I don't know. So only this sin theta would. Acha, sin theta to likha hi nahi na. Okay, sorry. There would be a sin theta as well, na? There would be a sin theta also, no? Because so you will get k q pi r square. What is integration of sin theta? This is minus cos theta. Don't forget it is minus cos theta from 0 to pi. So instead of writing from 0 to pi, what I would do? I would simply write kq upon pi r square. And then instead of this cos, I will simply write cos theta from 0 to pi. So this will give you k q upon pi r square. Cos 0 is 1 and cos pi is minus of minus. So you'll simply get 2 k, instead of k, what I will write? 1 upon 4 pi epsilon naught. So this, you will get 1 upon 4, pi square epsilon naught r square. So you will get q upon simply 2 pi square epsilon naught r square. Is that clear? I think this should be answer. Q upon 2 pi square epsilon naught r square. Right. This is the answer. Is that clear, Harshit?
Yes sir.
Okay, okay, good enough. So I'll give you another question, but let me wait for a few minutes. Just okay, now try to find another question. Try to find electric field again at the center only, but I will just give you some, like till now, the ring was uniformly charged. Now let us consider the case where ring is non-uniformly charged. Okay, so let us take a case for the non-uniform distribution of charge on the ring. So ring is non-uniformly charged. Okay, if the ring is non-uniformly charged, then what? Let us understand it by an example. Okay, so let us take an example where ring contains a linear charge density lambda. Let us consider a ring. अच्छा, इसको तो बना सकते हैं ना, 2 मिनट रुको. This I can make फटाफट से. Oh, this I could have done. Okay, so now next time I'll do it. So so let us consider this as a ring. Okay, and let us say, and this particular ring, I want to calculate electric field at the center only. So I want to calculate electric field at the center only. Okay, so I want to calculate electric field at the center only, and let us say this is my center. Okay, so here I have to calculate this. Given that this particular ring is a non-conducting ring, so let us take that this is a non-conducting ring. This you'll understand later on. Well, I'll teach you conductors, because in the conductors the charge gets uniformly distributed. So if I'm taking a non-conducting ring, that implies that charge would be non-uniformly distributed. And the form of the distribution is simply lambda is equal to lambda naught cos of phi, where angle is referred from the x-axis. Angle is referred from the x-axis. So angle is being referred from the x-axis, and let's say this is phi. This is your x-axis. Okay, this is your y-axis. Let's say, okay, and the charge density, the linear charge density on this ring is given by lambda is equal to lambda naught cos phi. Okay, and we want to find first, I'll do the difficult cases later on, but we want to find electric field at the center of the, we want to find electric field at the center of field. How would I find it? The first thing that comes to mind, that if this is phi, we know from trigonometry that in the first quadrant from 0 to pi by 2, your cos is positive. Okay, and cos behaves as a decreasing function. So basically exactly at 0 you will have a maximum, that is 1, and then pi by 2 it will decrease, and so on and so forth. So from 0 to pi by 2, you would find that your cos function would dictate that there would be heavy positively dense charges here, and then density would slowly decrease, and then you will have no charge exactly at this particular point, because at this particular point your phi would become pi by 2, and lambda is equal to lambda naught cos pi by 2. This would be simply 0. Is that clear? In the fourth quadrant also cos is positive. So here also you will find heavily dense positive charges here, and this density would slowly fade away, isn't it? Here
Yes,
you will
sir.
have strong negative charge density. Sorry, here you would have a strong negative charge density, and then this negative charge density would slowly. Here also you will have a strong negative charge density, and then this negative charge density would slowly fade away. Is that clear?
Yes, sir.
Okay, good enough. Now what would I do? So again, the same process. If I'm taking this as phi, I will just consider a small differential element d phi. I will just consider a small differential element d phi, and here you will have some charge. This charge I can write it as dq, which will be simply lambda into r into d phi. What is r into d phi? R into d phi is this arc length, which is r. So basically, lambda is a linear charge density. If you multiply linear charge density in with the length, you will get the total charge which is contained here. And you see, because here is a positive charge, here is a negative charge, what will happen? This positive, so it will push the whatever, let's say here, if I am try to find electric field here, so what will happen? This will push the uh, charge in this direction, right? So if I just place a 1 coulomb charge here, so it will push this in this direction, isn't it?
Sir.
Okay, good enough. And what will happen if I just think about a diametrically opposite corners? If I just take a diametrically opposite corner here, so because here there is a negative charge, it will also attract in this direction, isn't it?
Yes.
Okay, and so basically what will happen? So if I integrate from minus pi by 2 to plus pi by 2, so if I integrate from minus pi by 2 to plus pi by 2, what will happen? So if I integrate from, अच्छा अपन ने क्या किया था, 0 से pi by 2 से pi किया था ना, हाँ ठीक है. So lambda naught is equal to lambda naught cos phi लिया था ना, right? So what will happen? Let's say if I want to calculate the electric field at point O, what will happen? This will push this. If I just place a unit coulomb charge here, what will it do? It will push the electric. It will push the. Uh, you, you can say that the direction of the electric field would be in this direction. Okay. Now, if I just take a diametrically opposite corner here, diametrically opposite consideration, that if I just take here also a charge dq, first thing, this dq would be a negative charge, so basically it will attract. So your net electric field dE net. Okay, so this is one thing. Second, if I just take another charge from here, so what will happen? Okay, or otherwise what will happen? So okay, so if I just take another, for example, phi from here, and then again small d phi from here. Okay, again small d phi. So what will happen? It will push in this direction. So your net electric field would be in the horizontal direction, isn't it? So net electric field will be in this direction. And what it will be? It will be simply dE cos phi. Again, the same doubt you should understand. Uh, okay, sorry. The same thing one needs to understand is, just give me a minute, I think battery is down. Okay. Am I audible now? I don't think there is a problem with.
No, sir, there isn't.
Okay, good. So, what would happen? Eventually, if you just calculate the electric field for this particular hemisphere, entire hemisphere. Okay. So, what is clear, that the net electric field for this entire hemisphere will be dE cos phi. And then also you have to understand that with each of these positive charges, dq, there is there is another charge minus dq, which is also actually trying to, if you just want to find this electric field at point O, so you have to place a unit coulomb charge at point O. So basically this charge dq would be pushing this dq here, and this minus dq will also be attracting dq here only. So basically your net electric field will be 2 dE cos phi. Is that clear? It is not because I'm doing these two things. No, that is not the case. This is because if I want to integrate, if I want to find electric field for this hemisphere, the answer would be dE cos phi only. Because see, because of this charge dq and because of this charge dq, in totality, I'm writing dE cos phi. This is one. And secondly, also understand that if because of this hemisphere, if I want to find electric field, what will happen? So this will attract, it will attract a unit coulomb charge in this direction. This will attract unit coulomb in this direction, and overall, again this dE cos phi. So basically 2 dE cos phi. Is that clear?
Yes, sir.
And phi is varying from minus pi by 2 to plus pi by 2. So it will be k dq. Dq is r lambda d phi uh, divided by, I think, r square cos phi minus pi by 2 to plus pi by 2. Okay. So this will be 2 from minus pi by 2 to plus pi by 2. And this will be k lambda r upon r square would be there. And this is cos phi d phi. Cos phi d phi is simply sine phi from minus pi by 2 to plus pi by 2. And what it would be? It will be 2 k lambda upon r. And what is sine phi? Sine phi would give you, I think, sine phi pi by 2. I think there is a mistake somewhere. What? Sine phi ना, cos phi का इंटीग्रेशन क्या होता है? Sine phi होता है. and sine pi by 2 would be 1, sine minus pi by 2 would be again -1. So I think this would be 2. Let's take I2. Just give me a minute. कुछ गलती कर रही है in terms of, एक मिनट देखिए. Have I done a mistake somewhere? अच्छा, lambda was something else now. Lambda was given as lambda not cos phi. Sorry. So lambda not, that is why there is a mistake. Okay, sorry. So basically, what was the question? Question was not this. यहाँ तक तो ठीक है. So you have to write lambda is equal to lambda is equal. Did you get my point now?
हाँ सर, समझ आ गया.
ओके ना, वो एक्चुअली हम लोग लैम्डा सीधे लैम्डा को कांस्टेंट ही ले रहे हैं. लैम्डा कांस्टेंट थोड़ी, लैम्डा तो खुद भी फाई डिपेंडेंट है ना. सो एक मिनट रुको, इसको कैसे क्या करना है. सो आई हैव टू डिलीट इट. अरे यार, चलो देखते हैं. देखो, लैम्डा इज इक्वल टू लैम्डा नॉट कॉस फाई है ना, ध्यान नहीं दिए. तभी तो ये सब हो रहा है, तभी तो आधा हेमिस्फेयर पॉजिटिव है और आधा हेमिस्फेयर नेगेटिव है. बिकॉज आपकी जो चार्ज डेंसिटी वो किस पे डिपेंड कर रही है, फाई पे डिपेंड कर रही है, राइट. सो आधा हेमिस्फेयर पॉजिटिव होगा और आधा हेमिस्फेयर नेगेटिव होगा, बिकॉज द चार्ज डेंसिटी डिपेंड्स अपॉन cos phi. So from minus pi by 2 to plus pi by 2, I will be just taking these positive constants outside. So basically 2 capital K lambda upon R. So 2K lambda upon R, and not lambda, sorry, 2K upon R to bahar ho gaya. What is lambda? Lambda is simply lambda naught, and this is cos phi, and another cos phi would be there. So basically cos square phi d phi. Is that clear?
Yes sir.
Okay. So it means I'm writing 2K upon R and lambda naught also outside. What is cos square phi? I think if you just absorb this 2 inside, so 2 cos square phi is 1 plus cos 2 phi, right? D phi integrated from minus pi by 2 to plus pi by 2. Okay. So if I integrate cos 2 phi, cos 2 phi is simply sin 2 phi. And if I place pi by 2, so sin pi is 0 and sin minus pi is also 0. So this will give you K lambda naught upon R into simply pi. Okay, because this d phi would integrate, will give you phi, and pi by 2 minus of minus pi by 2, this is pi by 2. So your answer would be lambda naught upon, this pi would cancel, upon 4 epsilon naught R. Is that clear?
हाँ सर.
Okay ना, तो basically हुआ क्या था यहाँ, we are discussing a non-conducting ring. Okay, non-conducting ring means you are considering not the uniform distribution, rather the non-uniform distribution. So we are considering a non-uniform distribution. Is that clear? And that non-uniform distribution was given by lambda is equal to lambda naught cos of phi. And since cosine function is positive in the fourth quadrant and the first quadrant, so you have a positive charge density here, and here you have a negative charge density. Is that clear?
हाँ सर.
Okay, good enough. So I think this is enough for today. We will meet from tomorrow regular only, no? So we'll have class at 10:30 then. Okay, and we'll
ठीक है.
meet regular, not alternate now. So
Okay,
that, okay. So I hope it is fine ना, ये चीज समझ में तो आ गई ना?
हाँ सर.
चलो, good enough.
Thank you sir.
Okay.